Okay, week 4, COMP1521. I want to talk over the top of everybody. So today we get on to MIPS, assembler, and we'll be doing that for a week or two, and then move on to operating systems, networks, and the rest. Okay, so assignment 1, I'll have it out this week. It's due in week 7 now. Settle. As far as I know, the internal CSE survey, Mei Cheng sent out some mail about that. It's sitting there. Please give us some feedback. And someone asked me, I just noticed something on the website. Someone asked a question about the schedule, and I'd completely forgotten that week 10 has one of these annoying public holidays on the Monday, so we'll miss the lecture then. So I have to make up for it in week 13. And also, I think because of that public holiday, because there are labs on Monday, I think I decided we're just going to cancel all the labs that weekend so everyone stays in sync. That's the week I think that the assignment's due, so we'll add some extra consultation sessions for that week. Alright, quiz 2. As of midnight last night, 690 out of 750 people have done it. Don't know what the other 60 were doing, perhaps because I didn't remind them. Don't know. Most people got close to full marks, and remarkably, 8 people managed to score 0. Right. I don't know how you do that, but there you go. Even if you just randomly guess, you probably get 1 or 2 correct, but anyway. Right, so today, instruction set architecture is MIPS architecture and assembly language. Alright, here's some nerds. Anyone who was in COMP1527 last year, and I don't know why you're doing this course if you were in 1927 last year, but anyway, here's some more nerds. Oh yes. Just about visible. In fact, they're all nerds, you could argue, but I'm talking about the guy in the middle. Come on, 1927 people. You should be calling out. Anyway, I'll give you a clue. So, this guy slipped into relative obscurity after 1976. Why did he slip into relative obscurity? Because he was a little bit obsessed with doing things like collaborative computing, network computing, client-server computers, and the people he was working with thought, no, that's a silly idea. That will never do anything, never produce anything useful. Well, wrong they were, right he was. God, I'm sounding like Yoda. But his name's Doug Engelbart. So he started life as an electrical engineer, as did everyone in the early part of the 20th century. There were no computer scientists. But the things he invented, the list of things he invented, makes for quite interesting reading. So he invented the mouse, didn't invent the trackpad, but the mouse. Two-dimensional display editing. Remember some of those shots I showed you back from the 60s, most people were using teletypes, which are basically like an over-glorified typewriter. There was a stream of paper that went through, and the computer would print stuff, you'd type stuff in, would appear on the paper, and it went like that. So it was kind of like having a single hard copy terminal. But he came up with the idea of, hey, if we've got a display, why can't we edit it by moving around on the display? Duh! We do that every day now, but before then no one had thought of that idea. So obviously that led to things like Vim, gedit, and all of the editors that we use. Similarly, the idea of Windows-based interfaces predates whatever the Mac and Microsoft did in that space. The idea of hypermedia, where you've got documents that are somehow linked to each other. He wasn't doing it over the network, well, because there was no network back in those days. But this idea of documents that you can navigate from one document to another by clicking on links, no one else had come up with that idea either. He came up with it in the 60s, realised it to some extent, and of course that led on to the web. And the idea of collaborative group work, where you could have multiple people working on a single document. Okay, we all take it for granted, we've all got access to Google Docs or whatever, but once again we're talking about the 60s and the 70s, so that's nicely done. So because of all that work, he got the Turing Award, which, as I'll probably keep saying, is kind of like computer science's answer to the Nobel Prize. And also the very earliest computer network, the ARPANET, he had a second host, which effectively made it a network. If you've only got one host, you haven't really got a network. And just for fun, thank goodness the picture is there, unlike last time, here's the mouse, the original mouse that they built in 1963. You can see that it's got wheels to get the motion sensors and working out whereabouts on the table it is. That particular version there cost them about $50,000 to develop. So we can see that commodity mice these days don't cost anywhere near that. So really interesting guy, doesn't get enough credit, I don't think. Right, so let's head off into CPUs. Okay, so what we're dealing with now is we're dealing with a very simple device which has certain properties, and here I'm going to talk a little bit in general for a start, and then I'll talk specifically about what the MIPS architecture gives you. But a typical CPU is going to have a number of registers, a relatively small number, 32, 64, whatever. They're fast memory, they live on the CPU chip, and they're the place where data has to be before you can do stuff to it. If you want to get a value and you want to shift it left, you've got to have it in the register. If you want to add two values, they've both got to be in registers for certain kinds of architectures anyway. So every time I say something, someone will come up with a counter-example from a different architecture, but in any case, I'm trying to be a bit general here. So, a set of registers for manipulating data. There may also be a bunch of integer registers and a bunch of floating point registers. Then there will be control registers. The most important control register is the program counter, normally abbreviated to PC, which stores the current execution point for the program. There will be other types of registers. Typical kind of register might be a status register, where if you perform operations like addition, and if that produces an overflow, a bit will be switched on in the status register, which the programmer can interrogate if they're interested and discover that the overflow has occurred, or just ignore if they want to write programs that produce incorrect results. An arithmetic logic unit, which performs operations like add, subtract, multiply, divide, and or negate, XOR and shift. Okay, those kinds of operations. Also, a modern CPU obviously has to have access to a bulk storage system. The most important one is the random access memory, which will be an electronic thing which will be relatively fast to access, not as fast as the data registers, but often you can't directly act on things that are stored in the memory, and certainly that's the case for MIPS. So for MIPS, you have to load stuff from the memory into the registers, and then you can start doing stuff to it. And generally, a relatively simple set of instructions, where each instruction doesn't do very much. It might add two numbers together, or it might load a number from the memory into a register, or it might store a value from a register into a location in memory. So three typical kinds of instructions: transferring data between memory and the registers, obviously that's important. Computing values by sending a pair of values to the ALU and getting back a result, which is typically stored in another register. And also, very importantly, if you want to execute control structures like if and while, is a way of making tests and also of controlling where the execution of the program goes at a very low level, where you're basically saying things like, if this register contains a 0, change the program counter to this location here. Or maybe even an instruction that just says, change the program counter to this location, which would typically be called jump branch or something like that. So that's a very general statement, and particular processor architectures are going to have variations on that. So they may have a different number of registers, some might have 32, some might have 64, some might not have floating point registers on the CPU, there might be a separate floating point calculation unit. The registers might be 32 bits, or they might be 64 bits, which is becoming more and more common these days, and always a different processor architecture is going to have a different set of instructions to some other processor architecture. So if you want to try and work out a classification of architectures, you know, you have red wine and you have white wine, very broad categorization. You can do a similar kind of thing with CPUs, RISC and not KICS, CISC. So some architectures have a relatively small number of instructions. The instructions are very simple. Obviously, having simple instructions and not many of them means the hardware itself is going to be simpler. Potentially, each instruction can be executed faster because it's not doing very much. Of course, to implement a particular C program on a reduced instruction set computer is going to require more operations or more instructions than on a complex instruction set computer. So there's a whole lot of very well-known RISC architectures. MIPS is obviously one of them. ARM is a pretty well-known one, which I think they use that in COMP1521 as the processor. I can't remember. Anyway, so they're pretty well-known ones. So back in the late 80s and early 90s, there was this big argument about whether you should build computers with a reduced instruction set or whether you should make the instruction set complex. And the reason for making it complex is that you can encode lots of the typical kinds of things that you do in programming languages as single instructions. So a very common thing to do, add two variables together. The way you've got to do that in RISC, load the value of one variable into a register, load the value of the other variable into a register, then add them together, store the result in a register, and then potentially push that back out into the memory. So a complex instruction set computer might have a single instruction that says, take the value in this memory address, the value in this memory address, add them together, and put the result in another memory address. So much less code to be produced. The downside, of course, is that it's going to make the hardware more complex. So there was this argument about which is best. Nobody won, really. So we've got a lot of RISC architectures around these days. We've also got a lot of very common CISC architectures, for example. The Intel x86 family is an example of that. Now, when you say one's complex instructions, one's simple instructions, a RISC architecture might have 60, 64 instructions. A CISC one might have 128. So there's not a lot of difference, in fact. All right, so what do these instructions look like? Well, typically, and here I'm going to talk about 32 bits all the time because the MIPS architecture that we're looking at is the 32-bit one, which is the one that's available with the spin emulator. So if our instruction set was 32-bit instructions, then each instruction has some information in it. And typical kinds of things that you're going to find in an instruction is an operator. You're always going to find an operator of some sort, something like add. And then you may have a bunch of operands. And here I'm postulating, once these aren't real instructions from any known architecture, but they're just to give the idea of how these instructions fit together. So you're going to partition up the instruction word, partition up the 32 bits into a number of bit fields, if you like. We talked about bit fields last week. And how big you make this bit field here determines obviously how many different instructions you can have. So here we've got 8 bits, therefore we could have 256 different instructions. So we'll always have an operator. Maybe some operators like exit the program, doesn't have any arguments. It's simply an opcode and the rest of the 32 bits can be empty. But something like add is likely to have 2 operands. In the case of a RISC architecture, they'll probably be register addresses and a destination for where you want to store the result. Once again, a register address. Now you can see that we've got 8 bits for everything here, so clearly we'd be able to address 256 different registers in this architecture. That's probably a lot of registers, more than most architectures would have. So typically their register operand bit fields are going to be smaller than 8 bits. And we'll see that the MIPS has only 32 registers, so we don't even need 5 bits for each of those operand fields. And most machines will have different kinds of instructions. So here we've got an instruction that involves potentially 3 registers. Here we've got another instruction that involves a register where the data is going to be stored and an address or perhaps a literal value. And this operator could be something like load. So load into this destination register a value from here, or it could be load into this register a value that's currently stored at some address in memory. So that's the kind of flavour of things that happen. So how many bits we have to allocate for each of these things depends on how many things we've got in the hardware. If we've only got 64 different instructions, we'd only need 6 bits for the operator. If we've only got 32 registers, we'd only need 5 bits for each of these. So that would be 6 plus 15, 21 bits, then we got another 11 bits floating around to make up the 32 bits. What do we do with them? I don't know. We might be able to think of something. Alright, so common kinds of instructions that we find on these architectures: load the contents of a memory address into a register. Maybe load a constant value into a register. So the difference between these first 2 instructions would be here, one of them assumes that the final 16 bits refers to a memory address, the other one assumes that the final 16 bits refers to a constant value. Of course, having only 16 bits here puts a bit of a limit on the number of constant values that you can deal with. Oh, it also puts a limit on the size of the memory. The converse of load obviously is store, where you take a value that's in a register and push it out to a memory address. Other kinds of instructions: jump, which is what I was talking about before, where the argument to the jump instruction, the operand if you like, is a memory address, and it simply changes the value of the program counter to that particular memory address, therefore the program starts executing at that point. And invariably processors are going to have not just a straight jump, but some kind of jump that depends on the result of a test. So potentially you could have something like jump if some register equals 0 to a particular memory address. Other kinds of instructions, obviously, we want to have arithmetic instructions, so we want to be able to add things together, and you'd have subtract, multiply and divide. We want to be able to do bitwise AND and bitwise OR and bitwise XOR, negate, and shift operations. And generally there'll be some kind of special operations that allow you to access the supervisory part of the machine. Now, typical programs aren't going to run, you're not going to load a program onto a machine and it's going to run in isolation. Typically there's going to be some other code floating around to manage devices and so on. And syscall allows you to tap into that. And in the case of the MIPS emulator that we're using, syscall is the way that you can access units and do things like print and read. Okay, so when a program's executing, it operates like this, so potentially an infinite loop that just runs and runs and runs, and what it does, it loads. So let's treat the memory like a giant array of, in this case, 32-bit words, and we're going to load the word that's currently at the address indicated by PC. So there'll be some kind of instruction register in the CPU that value gets loaded into, and then always we're going to, well, potentially we're going to go and execute the next instruction. So we make that assumption and we increment the program counter by 4 to indicate that we're potentially the next instruction after the one that we just loaded is the next one that we want to execute. Alright, once we've got the instruction into some kind of instruction register, we've got to work out what does the instruction do, what are its operands, and effectively execute the instruction by taking those operands, feeding them possibly through the ALU, and getting a result back and storing it in the appropriate place. So that's what would happen under normal circumstances. Otherwise, if the instruction is some kind of special instruction like halt, then we break out of that loop and the processor would stop executing. Now, most machines are never going to do something like that. More likely, this might be in the current program, which would return control of the CPU back to the supervisory program and simply terminate the running program. Now, of course, it's possible that executing the instruction might be something like a jump, so that's actually going to modify the value that we stored in PC and we'll just change it to something else. So when we go around the loop again, we'll load the next instruction from whatever we set the program counter to. Yeah. Okay, so first thing, so when we're executing an instruction, we've got to determine what the operator is, and the value that we get from the operator generally tells us what kind of operands we're expecting. So there might be an add operator, which is expecting 3 registers as arguments, and of course the hardware has to know that, you know, the effect of executing the add instruction is to take the contents of this register, the contents of this register, add them together and store the result there. But of course there might be some other machine architecture which behaves like take this register, add them together and store the result in that one. If we've got a load instruction, then we know that the whole point of load is to take a value from memory, so we've got to have a memory address somewhere, so that'll typically be the last 16 bits, and the contents of that address is going to be loaded into that register. It's possible that this might be load C, in which case this value is going to be stored in that register. Right, so all that stuff I've been talking about, I've been using symbolic notation, add and load, but when it gets down to it, when the program's actually running on the machine, it's just a bunch of 32-bit bit strings, and they could look like that. So there's a sequence of instructions that could be doing something in some kind of machine, yeah?
Is the memory location referring to RAM or register?
RAM. Yeah. If that wasn't clear. Yeah, so something like that is going to be an address somewhere we're not talking about the memory, I'm always talking about the RAM. Okay. Alright, so when an executable program is loaded, it's just a bunch of 32-bit bit strings stored somewhere in the machine's memory. What I've been talking about with these symbolic kind of things is actually assembly language, which is a symbolic way of describing machine code. Now, you've been writing programs in C, that's a slightly higher level language where you can talk about things in terms of while loops and functions and assignment statements and so on. The kind of operations that you're dealing with at the machine level are much lower level than that. And so, even though they're lower level, it's useful to have a way of talking about them in some kind of symbolic form. We don't want to talk about executable, we don't want to talk about writing programs like this. That would be extremely tedious. That's the way they used to do it back in the 40s. We don't want to. So assembly languages provide a symbolic way of talking about those low level operations. So there's a very close mapping. Each assembly language instruction typically corresponds to one 32-bit machine instruction. And occasionally we'll talk about, I'll use the word assembler when I'm talking about assembly language, which is shorthand, but it's a slight notational abuse because often the word assembler is actually referring to the program that takes an assembly language program and turns it into binary that can then be loaded into the machine and executed. So machines don't directly execute assembly language. Assembly code is just a convenient way for us to look at machine code rather than trying to look at those binary bit strings. And we saw, I showed you a couple of weeks ago, you can run GCC, use the -S option, and that will take your C code and show you and produce corresponding assembly language code. I've forgotten what the architect, I think it might be x86 is in the lab, so it's producing assembly code for the Intel architecture. If you run GCC in the labs, and if I run it on my Mac, I get the same thing. If I was to use an ARM processor and do GCC, compile to that, then I get a totally different set of assembly language instructions. Alright, so what kind of symbolic niceness does assembly language provide for us? It allows us to write instructions using names rather than hex codes. So add and load and those kind of names that I've been using, they're relatively easy to understand. You can refer to registers rather than by bits. 5 bits as part of a hex word. You can use a symbolic name like register 0 or register 5. And you can also, one thing that assemblers do is they allow you to associate symbolic names to memory addresses. So you don't have to remember that this particular data object is stored at address hex 1000. You can give it a name and the assembler will take that name and associate it with the address. So that's one thing that the assembler does. Basically, you can fill your program with symbolic names. Once the assembler's done its job, all of those names are going to be converted into memory addresses, and that's what will be stored in the bit strings of the executable machine code. So writing programs in assembly language is quite different to writing them in C. In C, as I said, you've got some nice abstractions like functions and control structures. In assembly code, you're dealing with much lower level kinds of operations. So things like jump, load, store, add, and so on. The other thing about assembly code is, well, compared to what C gives you, with C you can define local variables which are magically created when a function is called. So you define a function f which has got a local variable int x. Whenever you call f, a version of x is created that you can start using. With an assembly language you don't get that. So you've got to manage all the memory yourself. You can simulate that behaviour, but you've got to program it yourself. Of course, we normally use a compiler, and a compiler is going to produce bits and pieces of code that simulate the behaviour of creating local variables when you invoke a function. If you're dealing with a RISC architecture, you've generally got to manipulate data in registers. Even CISC architectures, typically you've got to do some things in registers, and you don't have control structures at all. You've got to emulate control structures by writing tests and jumps, branches. So there's a long distance between what you do in C and what you do in assembler. And in the next couple of weeks we'll be looking at how you implement all of the different structures that you're used to in C, how you can actually implement them in assembly language. Alright, so MIPS. So MIPS is one particular CPU architecture, and in fact there are a whole lot of different versions of MIPS as well. There's MIPS 1, MIPS 2, MIPS 32, and now there's MIPS 64. So we'll be looking at MIPS 32, which is the one that works with the emulator that we've got, the SPIM emulator. MIPS was a very popular architecture back in the 90s. Silicon Graphics is one company that exploited the RISC architecture of MIPS very well. NEC, various gaming consoles also used MIPS processors, and they might well still do that. Also back in the 90s, there were a lot of supercomputers that were based on the MIPS architecture. Nowadays, they don't tend to be, or at least they might be based on having thousands of MIPS processors all working together. So nowadays we tend to get performance by having a lot of concurrency in the system. So anyway, we're going to look at MIPS 32. You can find plenty of information about that online, and I'll stick some of the documentation on the course website as well. So there was a very well-known emulator for MIPS called SPIM, which was written back around 2000, which has evolved over time, and recently they've added a graphical front end. So we're going to look at both versions of it. The SPIM command line based emulator is quite useful for testing, and Qt SPIM is the one that's already available on the CSE workstations, and it's also downloadable for every architecture known to man. So if you're running Windows, or you're running Mac, or you're running a flavour of Linux, you can download a binary version of the Qt SPIM system. Or you can be brave, download the source code and compile it up yourself, which is good fun. In any case, they're all available there. And I put a copy of the source code under the CS1521 website, so you can go and have a look at it. It's actually not too difficult to understand the code. It claims to be written in C++, but looking through it, I don't see a hell of a lot of C++ in it. It looks largely like C, except, all the source code files have got .cpp, but they look a lot like C to me. Anyway, so that might be an interesting thing. I was thinking this morning, maybe assignment 2 might be to write an emulator for a little architecture that we can invent. In any case, I'll think about that. So, yeah, if you want to have a look at a bit of moderately large C, see how it fits together, take a look at that. Alright, so what's special about the MIPS CPU? It's got 32 general purpose registers, each of which is 32 bits. It's also got 16, and to some extent this depends on how the system's configured. You can stick in a lot of co-processors alongside the CPU, so you might have a graphics co-processor, a floating point co-processor, and so on. But a typical MIPS CPU might have 16 double precision floating point registers. In fact, they can also be used as single precision floating point, and they come in pairs. So you've got floating point register 0, floating point register 1. You can treat them separately, but you can also treat them as a single 64-bit register. Obviously there's a program counter, and there are 2 special registers called high and low, which are basically used for multiplication and division computations. So if you're taking 2 32-bit quantities and you multiply them together, you're likely to get a value that's larger, that won't store in 32 bits. So when you do multiplication, it stores the entire 64-bit result in the pair of those high and low registers. And when you're doing division, it stores the quotient in one register and the remainder in another register, in the other register. I'll talk about which ones in particular later on. So you can refer to these registers using numbers. So I want to access register 0, I write $0 in my MIPS assembly language program. I want to access register 31, I write $31. Some of the registers are special in some ways. $0 is a register that always contains the value 0. Why do we do that? Because 0 tends to be a useful number to deal with when you're doing computation. 0 and 1 are probably the most common kind of numbers that you want to deal with. So register 0 is kind of like a read-only register. It only ever contains the value 0, so you can't load a different value into it. And some of the other registers are reserved for use by the supervisory system. So registers 1, 26 and 27. Alright, so let's take a look at the registers in a bit more detail. So register 0 always contains 0. Register 1, as I said, that's a special register. It's reserved certainly in the spin emulator for use by the assembler. Then registers 2, and to some extent, apart from the special registers, a lot of the way these registers are used is really just convention. They're all general purpose registers, and you can stick whatever you like into them and take it out and store it in memory. But the convention is that registers 2 and 3 are going to be used for function return values. So they're also called $V0 and $V1, which I assume is for return value. Also, typically they're often used for the result of evaluating a large expression. Then the next 4 registers are used for passing arguments to functions. So if you want to invoke a function, you load the value of the first parameter into register $A0. You load the value of the second parameter in $A1, the value of the third parameter $A2, the value of the fourth parameter, if you've got one, in $A3. What if you've got 5 parameters? Well, then you start pushing the excess ones onto the stack. So then the next registers, the next set of registers, temporary registers, as the name suggests, no one cares if they're overwritten, so you can just use them however you like in the process of computing results. So if you need to work out the sum of two numbers, you load one of the numbers into T0, load the other one into T1, add them together, store the result in T2, and then if the result has to go back into memory, then you store the result that ended up in T2 back to some memory address. Okay? So they're used for computing, intermediate stuff, and anyone can write over the top of them, and no one should assume that they're going to survive function calls. So in MIPS assembler and assembly language in general, there's no inherent notion of a function. So we don't call them functions generally, we call them subroutines. So basically what happens is that you're executing the code, you want to go to a subroutine, you execute a special jump operation that says go to a subroutine. The one thing that's a little bit specialised about jumping to a subroutine is that it will save a copy of the return address, so that when you're inside the function, you can go back to the point after which you made the function call. Okay? So there's a notion that some registers are just free for all, you can do whatever you like with them, and they're intended to be used on a temporary basis. Some of the others are required to persist through function calls. So the next set of 8 registers are registers that, if I'm executing a function and I've put values into these registers, and I then make a function call, or a subroutine call, when I come back from that, these registers should contain the values that they held before I jumped to the subroutine. Right, the subroutine is free to modify any registers it likes, but it should, if it's going to modify these registers, then it needs to save them somewhere and restore them before it returns. So the assumption is that whatever values you put in these registers, if you make a function or a subroutine call, when you come back, those values aren't changed. T8 and now, why they split the temporary registers up, I don't know. So we've got another 2 registers that are free for all, anyone can override. 26 and 27, I said they're special, they're for use by the kernel or the supervisory system that's running on the machine. And the top, I've got 2 register 30s, obviously that should be 31. 4 registers that are used for controlling or for implementing the impression that you've got function calls in the system. So you've got a stack pointer and a frame pointer, therefore storing stuff on the stack when you make a subroutine call. And as I mentioned before, register 31, when you make a call to a subroutine, you say jump and link, and what happens at that point is that the address of the next instruction, the thing that's currently in PC in fact, is stored in register 31. So that when you're inside the function, when you want to return from the function, you can simply say jump back to the location that's currently stored in register RO. Now of course what happens if one function makes call to another function, oops, we've overwritten the return address, but you've got to save the return address in the function, in the sub function. So, I mean, here you're dealing with if you like, a fixed set of global variables, and that's all you've got. So you've got to make sure that you use those global variables in some kind of disciplined way, and that's basically what they're trying to get at with these intentional usages of all of these registers. Floating point registers. Once again, there's a notional usage for these different kinds of floating point registers. Analogous to V0 and V1, we've got F0 and F2. Now the names that I'm using here, you can see that there's a bit of a gap. We've got $F2 and then $F4. That's because $F2 conceptually is actually two registers. It's 64 bits, and you can individually index those registers as $F2 and $F3. Okay. And similarly for $F0, we're really talking about a 64-bit register comprised of $F0 and $F1. So we've got temporary registers that can just get overwritten whenever you feel like it. For function arguments, so analogous to the $A registers, we're using these registers here for passing floating point arguments. Temporary registers, once again, used for expression evaluation. And registers that are like the $S registers that are guaranteed to contain the same value after the function call as they did when the function was called. And I keep calling them functions, I should be calling them subroutines. Right, so yeah, that's that point. So these registers come in pairs. So $F0, $F1 is a pair, $F2, $F3, and so on, and up to $F30, $F31. Okay, so getting down to the language that you actually write MIPS machine code in, if you like. It's a very simple language. Each line of the file either contains a comment or a directive or an instruction. So comments are introduced by hash, and then anything following the hash to the end of the line is ignored as far as being part of the program. You can specify labels, so these are the symbolic names that you can give to memory addresses. So they appear at the start of the line followed by a colon, and we'll see examples in a minute. Then there are special instructions that don't make it into the machine code. They're really telling stuff to the assembler. In some sense, they're kind of analogous to the C preprocessor thing. So hash include doesn't actually end up being compiled into some instruction. It simply tells the compiler to do something. So these directives are telling the assembler to do something, or they're telling it something about the code. And then, of course, you've got the actual instructions themselves. As a programmer, what do you need to do? If you want to have data objects that your program is manipulating, you have to say whereabouts they exist in memory. And if you're smart, you'll give them a name, so you can refer to that name in the rest of your code. And obviously, subroutines, functions, whatever you want to call them, sequences of instructions that do stuff, they do calculations, they set up results, and eventually they return. So, as we had with C, remember that the memory was partitioned up. We had the code segment, the data segment, the heap, then a gap, then the stack. Right? So MIPS has a similar kind of arrangement. We've got the code region and the data region, which are separate. And we also have a stack, but there are some other regions which I'll talk about in a moment. Right, so here's an example just to give you a feel for what's going on. Okay, so this thing here is a label. So we're just giving a name to a piece of memory. All of these names are global, so you need to be careful that you don't use the same name in a different part of your program. This says all the stuff that I'm about to define goes into the data segment of the memory. Okay, so it's stuff that's going to be manipulated as data. And This comment here says that all the rest of the stuff after this is going to be code, and therefore it goes into the code segment of the memory. I don't know, I haven't tried whether you can put .data, .text, .data, .text. Maybe you can. You can play with that and see what happens. The next directive here basically says main is a name that's going to be known globally. And here's where the name main is defined. So basically what's going to happen is the assembler sees .text and says, all right, what I'm seeing from now on, I'm going to put into the code region of memory. The first thing it sees, apart from .global, is main. And it says, all right, I'm at the start of the text region of memory, therefore the name main is going to be associated with the address of the start of the text region. And then it starts, and there's nothing in that text region yet, but you're defining that down here. Another directive that we've got up here, when you're defining stuff in the data region, you want to be able to either allocate some space, and there's a .space directive to do that, or maybe you want to allocate constant values. You want to stick a string or a number value into the memory. So this directive here will insert that string at the first location in the data segment. Okay, the assembler is going to treat .data kind of the way it treats .text. It sees .data and says, okay, from whatever I see from now on is going to be placed in the data segment, which always starts at a fixed location. I'll talk about that in a minute. The first thing it sees is a label, and it says, all right, this label is going to be associated with the start of the data segment. So whatever that happens to be, let's say it's 10,000. So the label message is going to be associated with the value 10,000. And what's going to be stored at the location 10,000 is this string here. And the fact that we've said ASCII Z means that it's going to be a null terminated string like you normally expect in C. So we're going to get all of those characters followed by a null character will be stored at the first location in the data segment. Alright, going back to the code. Alright, here's an instruction, a MIPS instruction that basically says, alright, LA is load address, and it takes two operands, one of which is a register, which is the destination, the other one of which is a value that represents an address. So it could be a name, or it could simply be a number. If you happen to know where the start of the data segment is, you can simply write the whole number value for that. Obviously it's much nicer if you've got a name that you can use. So what this is going to do, it's going to get this address, which is the address at the start of the data segment, and load that address into the register A0. So what this is actually doing, it's setting up an argument so that we can call a function, a special function, to use that argument. So in fact what we're doing is we're setting up a pointer to the start of this string. The next two lines are setting up for a system call. Now you just need to know, if I want to make a system call, I need to load into $V0 a number. And there's a bunch of numbers that specify different kinds of system calls. And it just so happens that the number 4 corresponds to the system call that will print a string, starting at the address that's been loaded into the register A0. So we say, all right, this is the kind of system call I want to make, and now I'm going to make that system call. So it's going to invoke the print function and use the contents of this register, which is effectively this address here, as the argument. And having completed that system call, we come back here and we do a special kind of jump function which uses the return address. So it assumes that the return address contains the place to go back to from where the function was called. And you might say, hey, that's a little bit strange. This is the main function, returning from the main function, well, where do you go? Well, in fact, the way that MIPS is structured, there's a chunk of code with the beautiful name $__start, which is where the MIPS code actually starts executing. And that's right at the start of the coded segment. And so that's going to invoke the main program. And then when we say JR$RA, we're going to return to the next instruction in the start segment after the call to main. Okay. So you can see we've got comments here. Anything starting with a hash is a comment and gets ignored. So we've created some data. We've created a couple of code instructions, and just to demonstrate that that actually works before we have a break. There's the code. I think it's similar. Actually, let's have a look. Yeah. Spaces aren't super significant, so it doesn't matter leaving it out there. And it turns out that if you leave out those commas, as long as you've got a space, the MIPS assembler is happy as well. So there's my MIPS assembler code, and if I want to run it, I can use the SPIM interpreter, and I have to say which assembly language file I'm reading from, and woohoo, it prints hello MIPS. Okay. It also prints this garbage, which I was very tempted to edit the code and get rid of, but I decided to leave it because when you use SPIM on the CSE workstations, which by the way hasn't yet been installed but will, it's going to print something like that at you all the time. So this is another chunk of code that also gets loaded into the interpreter, so if your program screws up, there's a way of handling the error. Right, so a very simple assembly language program, and let's stop right there for a break and we'll continue.